In section 2.2, we're going to be looking at metric spaces, something we'll keep talking about for the rest of this course. So let's go ahead and define this. A metric space is a set X a set X whose elements, what we call points, is a metric space if with any 2 points P and Q of X, there's an associated real number. Here we call this the distance between P and Q, such that the distance between any 2 points is always greater than, it should be greater than 0 if P is not equal to Q, and the distance is 0 only if the point is, we're taking the distance with itself, right? So this is sometimes called a distance function, right? Between any 2 points, well, there's a distance, it's always positive, or non-negative, I should say. Also, the distance between P and Q is equal to distance between Q and P. And here we have what we call the triangle inequality. The distance between P and Q is less than or equal to the distance between P and R plus distance between R and Q for any R in X. And like I said, this is called a distance function or a metric. Right, so again, we have a metric space if it's a set X, and these three properties, we have those three properties in our set with a distance function. So if you take in maybe a topology course, you know that metric spaces are a type of topological space. And we're going to be doing plenty of analysis in metric spaces. Okay, so the most important examples are in the Euclidean space, Rk. In the real line, maybe you've taken the Intro to Analysis course on the real line, R1, the distance function we use is just the absolute value between x and y. Right, so the distance between 4 and 6 is 2. That's the distance function we use, and as a matter of fact, we use it for all Euclidean spaces for Rk. So that's the example of the distance function. Also, by the segment AB, we mean the set of all real numbers x such that a is less than x, less than b. So that's just like maybe in high school you've heard of that, just an open interval, right, with the parentheses. But what does open even mean? Well, we'll see that right now. Also, we have a K-cell. You can go ahead and read the definition. I'm not going to read it. I'm just mostly going to explain the concept. So like on a real line, a K-cell would just be an interval. On a plane, on the Euclidean plane, a K-cell would be something like a square. In a Euclidean, in R3, this is 3D now, we would have a cube would be a K-cell. So that's what a K-cell is. But this is how you define it rigorously, right? We can't just say, we can't just explain what it is poorly with words and then just say that that's how we define K-cell. So this is what this is explaining, the definition of a K-cell in Rk, in Euclidean spaces. Also, here's where we define open or closed. If x is an element of Rk and r is greater than 0, r here stands for radius, the open or closed ball B with center at x with radius r is defined to be the set of all y in Rk such that the distance between y and x is less than r, or this is the case for closed, r is less than or greater than or equal to the distance between y and k. So all this means is we have for example, again, the R2 space. And we have our point X here. Then we define radius to be this length. Then we're including all these points of distance R, right? But not all those points. All those points and everything inside, right? Because all these Y points, let's do white and blue. That's a point of Y, just labeling them. But also on the edge only if R is the weak inequality. So basically, let me show you what that looks like. I have an example here that will look a lot prettier than my drawings. So an open interval, this is an R1. This would be an R2. That's what an open ball looks like. In R1, it just looks like an open interval. And R2 looks like an open disk. A closed one would be a closed interval on the real line in R1, and on R2 would be a closed disk. Right, so the only difference is that here we're not including the boundary. Here we are. With closed sets, we are. We include the endpoints. One definition that you may have heard before is convex. We call a set E of RK convex if lambda times x plus 1 minus lambda times y is an E whenever x and y are an E, and lambda is between 0 and 1. So maybe you know what convex is. Actually, I'm going to pull up a picture here of convex sets and non-convex sets. The reason this one isn't convex is because that line is outside of the set. So here, no matter in this set, the convex set, no matter where you draw a line, the line will be contained in the set. And this is actually how you define it rigorously. And with that definition, we can show that a set is convex or it's not convex. Okay, next we're going to define a bunch of things that you before. So first off, a neighborhood. We're going to let X be a metric space first. All points and sets mentioned below are understood to be elements and subsets of X. So a neighborhood of P is a set we denote as n sub r of P, consisting of all Q, such that the distance between P and Q is less than R for some R greater than 0. The number R is called the radius. So a neighborhood is kind of, well, basically exactly what it sounds like. Kind of like an open ball again. So like if this is our point P, a neighborhood of P would be this, but then we could also have this neighborhood of P or this neighborhood of P with a bigger radius, and so on and so forth. So the neighborhood is on analysis in the real line, neighborhood would be an interval, an open interval in this case because we have the strong inequality. A limit point. A point P is a limit point of the set E if every neighborhood of P contains a point that isn't itself contained in E. So these definitions, like I said, you should be familiar with them if you've taken analysis on the real line. Also, if P is an E and P is not a limit point of E, then P is an isolated point of E. And with these, you can try to come up with an example of these definitions, like a set. For example, a set of integers, those are all isolated points. Why? Because all those points, all the integers, or actually none of the integers are limit points of E. So they're all isolated points. E is closed, a set is closed, if every limit point of E is a point of E. That's how we define a closed set. An open set, oh, actually I don't have it yet, but a point P is an interior point of E if there's a neighborhood N of P such that N is contained in in E. So just what you would imagine a set E to be, its interior would just be whatever's inside. That's just how we define an interior point. If it's inside E, the way this is describing it is, for example, if this was E, then let's say this is P. That's an interior point because we can have a neighborhood, I'm going to draw like this, of P that's still contained in E. That's what that's saying. So that's why P is an interior point. But here, on the boundary, that wouldn't be an interior point because no matter how small I make the neighborhood, it's not completely contained in E. So that's why this bottom point is not an interior point. Next, there it is. E is open if every point of E is an interior point. The complement of E, denoted by E and then with that C at the top, is the set of all points P such that P is not an E. So exactly what it sounds like. So for example, if we had the set E, there's a closed one. This is all E, pretend it's filled in. The complement would be what's in red. EC would be everything else. That's not E. That would be the complement. This might be a new definition you've never heard before. E is perfect if E is closed and if every point of E is a limit point of E. E is bounded if there is a real number M and a point Q such that the distance between P and Q is less than M for all P and E. So exactly what it sounds like. Could draw a picture for that too. Let's say this is E. And let's just say this is P. Well, it's bounded because, say for example, this is the furthest point Q. We'll just make M even longer than that. Over here is M. So that radius around P, all the points in E are contained in that circle. So E is bounded. An example of something that's not bounded is the real line, because there's no number M such that P centered at P with radius M would contain the whole real line. So the real line is not bounded. And dense, E is dense in X if every point of X is a limit point of E or a point in E. Maybe you've heard before that the rationals are dense in the reals. That would fit the definition. Here we have three theorems that it's good to know the theorems. The proofs aren't as helpful, so I'm going to skip those. One, every neighborhood is an open set, and this one shouldn't be too hard to prove because we have this, like I had mentioned, this is not it's a strong inequality, not a weak one. Not a hard proof. if P is the limit point of a set E, then every neighborhood of P contains infinitely many points of E. That proof shouldn't be too hard either. Finally, a finite set has no limit points. That one should, I mean, intuitively, these should make sense, but of course, we can't just go off of that. We would need to show proof. But like I said, I'm going to skip these. They're not as constructive or actually as useful for this lesson. But we are going to move on to something to practice some of these definitions. So here, this column is a subset of R2. And we want to know if all those are closed, open, perfect, and bounded. So a set of complex Z, actually before we do that, go ahead and pause it and try to fill out the chart yourself. Using the definitions from the last slide. So remember, we're going to go over closed first. What does closed mean? Well, set E is closed if every limit point of that set is a point of E. So the set of all complex Z, such that absolute value is less than 1, is that closed? Well, no. Right? The boundary of that set would be limit points, and it's not contained in the set, so it's not closed. What about this next one? Is that one closed? This one is closed. This one's a solid circle. This one is a not a solid one, right? A dotted one. We're not including the boundary. A non-empty finite set, is that one closed? Does it contain all its known points? Well, it does, right? Because it has none. Set of all integers, also closed because it contains all its limit points since it has none. The set consisting of all the numbers 1 over n. Is this one closed? This one is not closed actually, because it doesn't contain 0, and 0 is a limit point of this set. What about the set of all complex numbers? This one is closed. And the segment AB, that one is not closed. The interval AB is not closed. All right, it's an open interval. Next, open. Is this set open? The first one? Well, yes, this one is. What about the next one? This one is not open, right? Because I had gone over that. Points on the boundary. You can't draw a neighborhood that's contained in that ball. A non-empty finite set is open. No. Same argument, just go off the definition of open. Set of all integers. No. The set consisting of the numbers 1 over n. Is this an open? Nope. What about the set of all complex numbers? This one is actually closed and open. And here's probably the tricky one, the segment AB. This one open. The answer is actually, we're going to leave it blank. And the reason we leave it blank is because AB is open in R1 but it's not open in R2. And I'll go over the reasoning shortly, but try to think of why that's the case. We're going to move on to perfect. Is this first set perfect? Well, it's not even closed, so no. This next one, is it perfect? Yes, it's closed and contains all its limit points. A non-empty finite set. Non-perfect. Are all its points a limit point? No. What about set of all integer? It's closed, but the integers are not limit points. So since also no. What about the set 1 over n? It's not even closed. What about the set of all complex numbers? This one is perfect, contains all its points are limit points. And finally, the segment open interval AB. That one is not even closed, so it's not perfect. Finally, bounded. This should probably be the easiest to figure out. So this one we're being bounded by 1. So yes. This one we can be bounded by 1.1 or any number greater than 1. So this one is also bounded. A non-empty finite set. So a finite set is always bounded. So this one is yes. The set of all integers. Do you think that one's bounded? That one's actually no. Right? The integers keep going on forever. The set consisting of 1 over n. 1 over n is actually a convergent sequence. And maybe you remember that in analysis on the real line. Convergent sequences are bounded. The set of all complex numbers is unbounded. That one is not bounded. And the segments AB, can you bound that? Well, of course. Right, it's just an interval. You can bound any interval AB. So that's our chart filled up. You can check which ones you got right and wrong and why. Okay, we move on to a theorem. And here I'm not going to be including proofs for all the theorems, although I will include some. Here, if we let E sub alpha be a finite or infinite collection of sets, then this equality holds. You may know it as De Morgan's law. Also, a set E is open if and only if its complement is closed. This is a pretty big theorem, so we're going to go over this proof. So for this one, I'll be drawing pictures to make our intuition, to help our intuition. So first, we're going to suppose the complement of E is closed. I want to choose a point X and E. So I'm just going to draw a picture down here. EC will be in red and E will be in blue. So let me draw a picture. So E complements is everything outside, all this. E is everything inside right here, but it's dotted because actually we don't know that it's dotted, but I'm just going to draw dotted because I already know how this proof works out. Okay. So again, E complements is everything outside over here, and E is the inside. Okay, we're going to choose a point X in E. X, let's choose this point, X. Okay. Well then X is definitely not an E complement. Right, why is it not an E complement? Well, because E complement, we're assuming it's closed, so it should contain all its limit points. So X is not a limit point of E complement, right? And if X is in E, well, then it's not in its complement. So what does that tell us? Well, if it's not a limit point of it, there's a neighborhood N. Let's draw that neighborhood with green. And here. And Rx, that's a neighborhood of X. That's contained in E. Such that that neighborhood, the intersection between that neighborhood and E complement, what's in red, is empty, right? Therefore, X is an interior point of E, and E is open, right? Because this works for an arbitrary point X in E. So E is now open. That's why I drew that little dotted thing. I dotted set in blue. So we just showed that if E complement is closed, then E is open. Now for the converse, suppose E is open, and let me draw this picture again. I don't want to delete everything. It's just like that. So suppose E is open, let X be a limit point of E complement. So that means it should probably be somewhere here, right? X is somewhere there, because it will be a limit point of E complement. Well, then every neighborhood of X contains a point of E complement. So I'm going to draw that neighborhood. No matter how small we make this neighborhood, since it's a limit point of E complement, there's another point of E complement in there, in that neighborhood here. So X is not an interior point of E. And since E is open, this means that X must be in E complement. Since it's not an interior point of E, since E is open, therefore that shows that E complement is closed, right? Because X is not in E, it's an E complement, and it's a limit point of E complement, and again, arbitrary X. So E complement contains all its limit points, therefore E complement is closed if E is open. So again, we just showed both directions. Therefore, set E is open if and only if its complement is closed. So this next theorem, a set F is closed if and only if its complement is open. That one really, you just prove that almost exactly the same, just kind of doing the complements. Let me erase this so I can make space or not block whatever's next. Oh, these dots are going to take a while. Okay. There you go. So up next are pretty important theorems you might see even in a topology class. But again, I'm omitting the proof. You can go ahead and look for the proofs. Shouldn't be too hard, and they're not long either. But here, I just want to make an important distinction. Just going over them. So A says for any collection, G sub alpha of open sets, the union of all those sets is open. For any collection F sub alpha of closed sets, the intersection of all those sets is closed. And now here is an important word. For any finite collection, G1 to Gn of open sets, the intersection is open. Why finite? Well, because if we had infinite, we could actually have that their intersection is closed. And you can go ahead and come up with an example. I'll give you a little hint on a real line. Make nested open intervals and keep closing in on a point. that should show you that their infinite intersection is closed rather than open. So that's why we use it for a finite collection. Same thing for the D, for any finite collection, F1 to Fn, of closed sets, their union is closed. And again, that's not necessarily true for infinite collection. That's why the finite is really important there. So moving on to our last slide, we're going to define something called closure. And no, it's not what you think you need with your ex-boyfriend or ex-girlfriend. There's something else. So if X is a metric space, if E is an X, and if E apostrophe denotes the set of all limit points of E in X, then the closure is the union of the set E and its limit points. And we denote the closure with that bar on top, this bar here. That's how we write closure of E. So again, it's just a union of the set and its limit points. That's the closure of a set. So here we have some little theorems. If X is a metric space and E is a subset of X, then the closure of E is closed. Also, the set E is equal to its closure if and only if E is closed. And the closure of E is contained in F for every closed set F in X, such that E is also in F. Fairly straightforward proofs. For A, we're going to first assume, if that P is in X and P is not in the closure of E, well then P can't definitely can't be a point in E nor a limit point of E, right? Otherwise it would be in its closure. Well, therefore P has a neighborhood which does not intersect E. How do we know this? Well, because otherwise P would be a limit point of E. So the complement of the closure of E is therefore open. Therefore, the closure of E is closed, right? We're using that theorem from the last slide. Now for B, we're going to assume, or we're going to have that if E is equal to the closure of E, then E is closed. Well, if E is closed, then its limit points, it contains its limit points by definition. So E apostrophe, its limit points, is contained in E. Therefore, the closure of E is equal to E. Last one. If F is closed and E is contained in F, well then F contains all its limit points. Therefore, all the limit points of E are also contained in F. Therefore, the closure of E is also in F. So before ending this section, I want to go over that example that I said that the segment AB is open. Actually, let me make it just a more concrete example. We'll just go with the open interval 0, 1. 0, 1 on a plane would look something like this, where 1 is right here. That's an open dot, open dot. So on the real line, that's an open set. All right, I'll draw it on the real line over here. Why? Well, because any point you get, say as close over here as you can, you can still draw a neighborhood or get a neighborhood of that point that's still contained in the interval. So that's why in R1 it's open. You can always do that. But in R2, why is it not open? Well, because let's just take a arbitrary point X here. If you draw a neighborhood, yes, to the sides of it, to left and right, there are points of the interval, but above it, so let me zoom that in. Let's say we have this point X. This is a neighborhood. It looks a bit ugly. So again, this is our point X. And that's a neighborhood of X. Well, notice this point here actually ignore that. This neighborhood is not completely contained in the interval 0, 1. Why? Because there's still all this other space that I'm going to put in blue to account for in R2. So that neighborhood of X is not completely contained in the interval in R2. In R1 it was because we're just dealing with the line. In R2 though, in a plane, that open interval 0, 1 is not complete. Is not open in R2. So for example, if we were to have R1 be equal to Y, R2 equal to X, and let's say set E is equal to the interval AB, we say E is open relative to Y because E is open in Y, but E is not open in X. So that's when we say, well, E is open relative to Y because it's open in Y, but it's not open in X. So that's why we introduce that word relative. Right, so I guess to be explicit, we say that E is open relative to Y if to each P and E there's associated R greater than 0, such that if we have a point, say Q and E, in a distance between P and Q less than R is contained in Y, or that distance is contained in Y, and Q is a member of Y. I know this is a bit too much, I'm just saying it, I didn't write it down. But I'll make sure to mention it the next lecture, which is where we'll be using it when we're talking about compact sets. Finally, we have that we let E be a non-empty set of real numbers, which is bounded above. We're going to let Y equal the supremum of E. Well, then Y is in the closure of E. Hence, Y is an E if E is closed. So it's a little proof. So if Y is in E, well then Y is definitely in the closure. So assume Y is not in E. Then for every H greater than 0, there exists a point X in E such that this inequality holds. And why does it hold? Well, because y minus h would be an upper bound of E. If that inequality did not hold, therefore y must be a limit point of E. Therefore y is in the closure of E. So what does that tell us? That y is in E if E is closed, or that this theorem holds if y is a supremum of E, and y is in the closure, or then y is in E if E is closed. And that should conclude our section for metric spaces. The next section, compact spaces, or compact sets actually, will probably be, I shouldn't say most confusing, but pretty involved, but also extremely important in our study of analysis, especially when dealing with continuity, which we'll see in chapter 4. But this concludes our lecture for metric spaces.